Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, so today I got this Class A amplifier. I really want to build a Class A, and so I've got a bunch of parts and a couple board. Wait, hold on a sec. Wrong video. Yeah, just fooling. That's going to be the next video. This guy is a PFC, power factor correction. Actually, active power factor correction. There is passive power factor correction that you can do, and I really need to do a video of that. I had a viewer request that, and I really want to do that. But right now I kind of want to jump into a power supply design. These guys used to be, not trivial. They kind of are now. They're almost trivial now. The PFC portion of it, especially. These guys are essentially just a boost regulator. Very robust, very simple designs, just workhorses. And this chip on here, I've been reviewing PFCs lately. I want to design a high power one, and I just found this in a box. I've been cleaning out my storage here, and I've just found this guy. This guy's a Rev A. They have a Rev B out now. It's $150 if you want to buy one from TI. Anyway, I've had this around for a while. And the cool thing about this guy, it's only an 8-pin control chip. That's it. I'm going to bring you over here and show you a close-up of all this stuff, and we're going to look at the schematic and all that, so let's just do that. But yeah, so okay, so if you're not sure what PFC is, I'm going to kind of run a quick review on that too, guys. But basically, for an audio amplifier, for sure, it's common that you take a bridge rectifier, big old guys like this, take the AC, run it through there, make pulsating DC, and run it through these caps and make a nice stiff DC power supply, okay? And you use big caps, and there's issues with that. You have to put in, they call it VA, they don't call it watts, it's volts times amps. Well, that's watts, but not when it's AC power going through a rectifier. They refer to it as VA because they want you to know that if you want, say, 360 watts, then you're going to probably have to put 600 VA into it. You're not using all that as real power. That's where you get real apparent and reactive power, all that kind of stuff. That's your power factor stuff. I should do a video on that, right? But that's basically when your sine wave voltage and your current is not in phase with each other. That's the simple way. But it actually gets more complex because when it goes to a rectifier, this current's not a sine wave anymore. That's part of the problem. Not only they are not in phase, but the current's not sinusoidal. It's got big old pulses. When the diodes finally do conduct, when the voltage, when they get forward biased, when they get above the output voltage, they have to send the current for a short amount of time. So it's a big, almost square wave with a big peak on the end. So sharp edges, DVDT, fast rising edges, are on voltage or current. It's not good for EMI. And power factor correction not only puts them in phase, but it tries to make the current look more sinusoidal. So it has some fuzziness, you'll see it. It's not perfect. But you know what? It doesn't take a very big EMI filter to fix it up. So let's come over here and take a look. Actually, I'm going to pull up a board, and we're going to go over, and I'm going to review this just for a moment, okay? Sorry. Let's do that, and then we'll come over here. So normal AC power supply, AC to DC, you'd go through a bridge rectifier, right? 4 diodes, steer the current, so you get this AC voltage. But I got this little dotted one here because these rectifier diodes would flip this guy over, so all the positive cycles are going up here and negative cycles this way. So you get a polarized cap out here, big old bulk capacitor, and that's how you convert AC to DC, right? Well, when you do that, now I kind of show this red dotted line as the output voltage. So as the AC signal comes up and the peak of it goes above what this thing's charged for, it turns on one of these diodes. And as it does, like on this half the waveform, it turn on, say, this diode. So as it does, there's a big peak inrush current, and then it turns off as soon as this cap charges up to that voltage. And there's only about, 0.7, maybe a 1 volt drop, depending on the kind of diode you have. Well, then this waveform gets flipped over by this diode, and it gets put here up on top too. So you get this waveform, and then you get another big old peak pulse of current. Okay, so current waveform doesn't look so great. It causes EMI because you got these, and also the peak currents are very high because you have to get a lot of current in a short amount of time. All right, now let's see what a PFC does. All right, guys, I'm back. What I have is I've inserted our PFC circuit into our AC to DC power supply. So in between our rectifier and our bulk capacitor, now we have a boost converter. And it's a boost converter because it always has to be regulating. It always has to have current going to the inductor. So your output voltage has to be higher than your input voltage. And it's not your RMS of your input voltage. It has to be higher than your peak of the RMS voltage. So in this case, with the universal input of 265 volts RMS, which that's like, it's like 374 volts peak. Yeah, so this guy's putting out 390 volts. Okay, so the way it works, your three main components is your boost inductor, your diode, and your transistor. Well, I guess there's four because your control IC. In this case, we're using that TI 8-pin, really simplified controller chip. And he's going to turn this guy on and off. When he turns it on, he's going to charge current up into the inductor. When he turns off, the inductor is going to push, the current to the diode, discharge the inductor. But you don't want to discharge the inductor all the way. You want to turn this back on, charge it back up before it does that. And that's, so you have continuous current in this inductor. It never drops below, like I call it running dry. So it never runs dry. It's always got current in it. That's continuous mode conduction, okay? When it's in continuous mode, it's kind of like the example of pushing a car. If somebody pops the clutch and you stop the car, you have to get going again. But if they pop it and just before the car stops, they put the clutch back in so you can keep that car going to let them try to start it a couple of times. It's kind of like that. When you come to a full stop, you have to charge that inductor up a couple of cycles to get it operating before things, work as well. So continuous mode conduction is what we like. Now, what happens when you pull this guy off and you pull current and you charge up that inductor, this diode's reverse biased. You don't want too much leakage current. You don't want any leakage current going through that diode. That just heats up that diode. So, and it wastes energy. So this diode, silicon carbide diode, good diode to have there, no leakage current. Okay, so you got those components chosen. And then the other components you can see here is I have two resistors, kind of showing what the voltage feedback might look like. Now, because it's high voltage, this resistor here is probably several resistors. And this voltage down here is a low voltage, so one resistor is down there. But anyway, you're dividing the voltage so you can give your voltage feedback to this control chip so it can change the duty cycle and control the current. Now this guy here, as the current's going through the load, through the bulk capacitors, all this stuff, it goes back through here and goes to the current sense resistor before it goes back to the bridge, the diodes. Okay, so this guy here is going to let the chip monitor how much current we have, and this control chip is the average mode controller. So what it does is to kind of make itself not noise sensitive, to make it more immune to the maybe noise going on. It integrates, so it kind of squishes all that energy together and regulates off the current that way. But cycle by cycle, it's looking at the current. If you have a single cycle too high a current, it'll go into current limit control and stop the pulses to the transistor. As the current's coming this way, here's the ground reference to the chip, and the current's going this way, so this plus to minus, right? So yes, this signal going into the chip is always going to be minus. The amplifier monitoring that voltage off that resistor is set up to look at a negative voltage there, okay? Alright, so that's kind of how this guy works. Now, I drew this as kind of like the input voltage, So your voltage is your black, and instead of having a spike of current like in the previous circuit, now we're going to see a bunch of spikes, and then hopefully that's integrated. There'll be a small capacitor here, and hopefully that small capacitor can integrate it back together. So if you kind of know how a Class D audio amplifier works, when you have a whole bunch of pulses and you can create a sine wave or waves, that's kind of what's happening here. Is you're using current even all the way down here, even though the capacitor is charged way above the input voltage, you're taking current all the way across this the voltage. And this is where the diode's flipped it up, right? So all the current's positive. So out here all the current's positive, but over here the current's being taken from the input supply pretty evenly with the input voltage. Okay, so let me just point out one thing that's kind of an advanced feature of this chip. It's only 8 pins, so it seems very simple. There's some magic going on in this chip. A lot of times these kind of PFC chips, they have to look at the input voltage because they have to look at this waveform so they know when to switch the transistor on, so they can reassemble this current like this. Well, this chip, what it does is it's looking at the output voltage coming back, and it's looking at the current here, and because an inductor, it's going to have, there's an equation, V equals L di dt. Well, the only thing, the L's not changing, and the di is going to change only on the ramp of the inductor. The di dt, as long as the switching frequency and all that's the same, then that part stays the same. So really the V in the equation is the only thing changing. So as it sees this voltage changing over here and the current here, it kind of knows it kind of can detect this signal. Okay, it does all that internally, and so there's only 8 pins. It's pretty easy chip to run. You have to put some voltage, like say 12 volts in to make it run, and then you have some feedback pins, and there's a couple more pins you set up the switching frequency, and that's 8 pins. Not too many. Alright, hey, let's go look at the signals. I think what we're going to do is we're going to look at this signal right here. We're going to watch this thing switch, okay? And then I think we'll maybe come up here. Now remember, this is called, I've done some other power supply videos, switching power supplies, some boost converter, actually, I'll put a link to one of them below. But this guy right here is your switching node, because that's the one that's going to pull down and let go. Pull down, let go. So this guy here is changing a lot of volts, okay? Everything else, this guy's kind of being regulated. This guy's changing slowly. This guy's changing with your switching frequency. That's your switching node. Alright, let's go look at some signals. Okay guys, and let's just look over the schematic real quick. Input comes through a fuse, MOV, and a 0.47 mic polycap. And then we have the combo choke and another 0.47 polycap and 2 caps that go to earth ground. That's our Y capacitors, or combo caps go with the combo choke. Then we have our bridge rectifier. Oh, there's a thermistor here, okay. And then we have our rectifier and a 0.33 mic cap. That small 0.33 microfarad is kind of our bulk capacitor, believe it or not, and that's for smoothing out the ripple from our boost converter right here, okay. And then there's our current sense resistor. So current goes through this inductor, our boost inductor, our diode, and out, and then back to the load, back to this current sense resistor. This is our switching transistor that pulls current through that choke and then lets go, and lets it go through this diode. Now you're looking at this diode. That diode is to allow current come through the rectifier and charge up this bulk capacitor. So the boost converter doesn't even have to charge it from initial 0 voltage. The current will come through, it'll start to charge up that capacitor before the switcher even starts kicking on. And then we have our 2 small 1 mic filter capacitors for the output. Then our voltage feedback goes to these resistors, and this resistor divider comes back into the voltage sense. And the current is picked up off this current sense resistor right here down this line. That resistor is to kind of limit current pulses. It's picked up right here to our I sense. So our control chip right here has voltage feedback and the current feedback. And then it has a resistor to set the frequency, switching frequency, and a VCC input that has 12 volts coming in. So yeah, you can see there's not a whole lot going on. It's fairly easy to set up. Okay guys, let's just go over the board here. What we have is our input circuit. It goes through a fuse. There's the MOV right there. Here's the 2.47 mic caps. And the black things are, they're Panasonic capacitors, just by the way. And this is a combo choke. And then here's those two Y capacitors going back to the E terminal. And then we have our thermistor right down here. Then this is our 12 volt input, just happens to be on that side of the card. So that's our input voltages, okay? And then over here is our output. And here's our big bulk capacitor and our boost inductor, and here's that 0.33 mic cap. So this diode is the one that's strapped across the input to charge up this cap, to help charge it up. Alright, let me turn this way so you can see it better. Here's a bridge rectifier, and over here's the switching FET back in there. Then down in there's that diode, the one that comes off the boost inductor. Okay, so those are the main heat conducting parts, the input bridge and these two guys. And then that capacitor right there, you can see right there, that little M with the symbol around it, black, silver, I can tell when I see that. It's a Panasonic capacitor, 85 degree, 270 microfarad, 450 volt. Okay, now let's switch over and look at the controller part. Okay, let me just kind of show you. Here's the input connector right here. Neutral, line, and E for ground. So those Y capacitors right there. Okay, and then our controller down here, our output over here. And this is our 12 volt input. Okay, now if you watch this neutral line, it comes in here, and our combo choke are these two big pins and these two. So it goes over here, then out here over to that AC. That's our neutral. Our line comes over to this pin, jumps over to fuse over here, and then comes down here and goes to the combo choke. Comes around here and goes through that thermistor, and then over to the AC. Alright, so let me see if I can walk you through this. This guy right here, this is our return side, our negative return up here for our AC, and there's that current sense resistor. So see, he's a nice size resistor, and he comes over this big old pad here, but see this trace right here? He's the one that's on the diode side, and he comes over here, he's on a jumper on the other side of the board, and he comes down this trace, and he's next around here, and then he goes underneath that resistor there, and then up here to current sense of this control IC, and there's a test point right there. Now over here, our output voltage, you can see there's one of the filter caps right there. There's some little test pins. I guess I didn't need to put it here. I could have grabbed those. Anyway, see this little trace that takes off? It's our voltage feedback. It comes around through those resistors. This is our resistor divider. Comes through here, and then runs along this trace and comes over to the voltage sense into that chip. And there's the voltage sense test pin. There's one of the filter caps there, and there's one there that we saw in the schematic. Okay guys, this is a power cable I made on another AC power supply I made one time for an audio amplifier. Just borrowed the cord because I use that to power this guy up. Has a switch here, and then it has a fuse, and I can plug into the board right here. Okay, and then on this end I got the thermistor, just another thermistor, just for a little extra safety. I think that's like 10 ohms when he's cold. Okay guys, so I just screwed those in there. Now what I'm going to do is I'm going to flip the board over, because I want to just be able to probe these guys. I think I'm going to rotate it around this way. I have my switch order on this side. Yeah, I think I'll do that way. Alright, so then I just bring my 12 volts from my lap supply into here, minus and positive. And then on this side, I'll put the load, and it doesn't really matter polarity, but put the red and black there. That goes to my load bank. Then there's the Hubble test meter. Alright guys, I just want to show you something what I do. I just had it turned on. I use a shield like this. I just put down a piece of plastic just until I feel comfortable, because I don't like things blowing up in my face. Now, see that fuse? I had the output. I actually shorted the output, took out the fuse. So, yeah, this power supply is pretty robust. It withstood my craziness and still works. Okay, so it's discharging. And here, let me go ahead and put a load on it. Power up the switch. The Hubble test meter goes red, saying I got high voltage there. So it's a safety feature of these cheap meters. I like them. Anyway, okay, so 384 volts, pretty high. Okay, let's go look at the scope. I just wanted to show you how that works there. And my load drains it off pretty fast. Okay, let's go take a look at the scope. Just before we go to the scope, in case you're curious, that's what the load bank looks like. Okay, and I just wanted to go over the rest of the setup. I took the Handtech, and it's just coupled on one of the AC lines down here. It's ×10 position. There's my on-off switch. These two probes are going to the gate. That is coming off of the Pintec differential probe. The mix sig is looking at our rectifier. It's looking at the plus voltage coming off the rectifier, so it's going to be seeing our rectified AC. And both returns are on this ground pin. The Pintec set at ×20, the mix sig is set at ×50. And there's our Hubble test set to look at our, our DC voltage. Look, it's flashing, saying hook up these inlets. You know, it's got some safety features as well as what you saw before, how it, when I turn it on, see, it turns 383, turns red. And then the load takes it right back down. So you got to be careful, guys, when you're working around this kind of stuff. These AC voltages, you got to be careful. What I do until I'm really sure about my setup is I use a piece of plastic like this to set over top of things. So if things blow up, and I have some safety glasses too, but yeah, I like to put something like this just so it's not coming up in my face. But you want to make sure you discharge your voltage. High voltage DC, anything above 30-40 volts can be dangerous, guys. So yeah. And there's my fuse. I had to solder this fuse on this side of the board. I did a bonehead thing, and I shorted out my load and took out the other fuse. But eval card's nice and strong and staying in there. All right, I'm going to hit the power switch, and we should see it pop on. Wow, little current surge there, no biggie. See that? That's the current channel 2, so it had a negative pulse and a positive pulse, and those thermistors kind of help that a little bit. And that's just charging those bulk capacitors, guys. Remember how we have that diode strapped across? That's what happens. That diode is turned on, and now the switcher starts to run. You can see the switcher turning on, some switching noise. Okay, let's adjust the current level, and we should see some more triggering. Okay, you know what? I'm going to zero out the meter. Alright, so I turned off the gate so that we could see the current and the voltage, and you can see how, we get like this dead time distortion kind of right there, right where the crossover point is. Okay, now what I want to do is I want to zoom in. Wow, I got to spread that out a little bit more. Okay, see the brackets up there? That's what we see here. Okay, let's look at the trough, okay? Let's bring that over, put the trough right in the middle. See right there, the crossover distortion spot? Okay, that's right at the minimum point, right? Now let's turn on the gate and zoom in on that and see what it looks like. I mean, look at that. There's not very much current there, so the gate is on quite a bit of the time and it's off. So it's on. Here, I got the cursor. See how long it's on and then it's off? Here, let me turn the cursor box back on and let's get the cursors over there. Here, I'll spread it out a little bit. Okay, let's get the cursor right there. And then the other one on. Okay, then I'll put the other cursor right about here so they're on the same part of the curve right there. It's about 8.46 microseconds. And if I go here, it's about 118 kilohertz. So if I go back to time, let's move this guy over to see how long the gate's on. So that's the time the gate's on, and then it's off, and it's on. So wow, look at that. It's on quite a bit of the time. Most of the time. Okay, if I go to duty cycle, does that tell me a duty cycle? So yeah, it's on 84% of the time. That's quite a bit. Okay, let's go to a different part of the curve. Okay, let's go to the peak. Here I'm going to zoom out because it makes it easier to scroll over. And let's put the brackets around the peak of this waveform right here. Okay, right here. That's the peak. Zoom in on that. Whoop, let's turn on the gate. Now look, now the gate's, it's getting closer to 50%. All right, so now let's go to kind of in the middle of the waveform. Let's turn off the gate so we can see it a little bit easier. Yeah, I'll move over to the middle of the waveform. Kind of between a peak and a valley. And we'll zoom in on that and turn on the gate. Okay, so now you can see that it's, you know, you kind of see how it's changing to the waveform, right? And that's how it kind of recreates this, sinusoidal. Here, let me turn this off. That's how it's kind of trying to draw current through the whole waveform to try to recreate the sinusoidal waveform. Hey guys, what do you think? Hey, by the way, if you haven't subscribed, please do so and hit the thumbs up. That helps the video. That helps me a lot. And throw out a thanks to the Patreons and anybody, you know, helping on the PayPal. That's really nice of you guys. Links are down below for that stuff. So what do you guys think of this stuff? Pretty cool, right? Oh, and this TI board, by the way, I think you can buy it now for 150 bucks on Mauser. Not cheap, but, you know, it's pretty cool for an eval if you're trying to design something like this. But you can also buy the parts and build it yourself for much less money. Pretty cool, right? Hey, let me know what you guys think, what other signals you'd like to see, what you'd like to see me do with this. The other thing is, or any more explanations you'd like to have. Another thing I like to do is connect this up to a power supply that would run like, say, an audio amplifier. So have to design something like that, right? Hey, thanks for watching, and we'll see you next time.